Good afternoon, everyone. Thank you very much, Esther. I think this is exactly what we needed for the coming session, because we have been talking mostly about theories and tools since morning, and this time it's my pleasure to open the next section about applications. And due to this topic, I would like to gently remind the speakers to save some time, if possible, for the questions, because we can expect, I think, many questions in this section. And it is my great honor to invite the keynote speaker of this section, Professor Christian Huck. Professor Huck currently holds a full professor position at the Institute of Analytical Chemistry and Biochemistry at Leopold Franzens University in Zug, Austria. And he has been working with various analytical technologies, including NIR spectroscopy. And Professor Huck received the Thomas Hirschfeld Award last summer. And he is also well known about the editorship of NIR News. And today he will talk about a recent trend in NIR spectroscopy, including quantum chemistry and two-dimensional correlation spectroscopy, and its future potential for aquaphotomics. Professor Huck, please deliver your lecture.
Thank you very much for this very kind introduction. Let me start off by saying what a pleasure it is talking to you today. I'm going to be spending approximately the next 30 minutes giving you an idea about how to implement quantum chemical calculation, 2D correlation spectroscopy next to conventional NIR spectroscopy, even for the application in the aquaphotomics field. Now, at first, let me start with a little bit an introduction where we are. So, Innsbruck is located in the heart of the Alps. So we are very close to Munich here in the south. You can go very fast, only about 30 kilometers to Italy. So we are really in the middle of Europe. And this is the view almost the same as from our laboratory. So Innsbruck is the heart of the Alps, and by looking out of the window you can already see here the mountains in the north, and I always say when I look out of the window I have the feeling I can already see some NIR spectra. This is our famous roof. It's called the Golden Roof. It was installed by the former emperor in the 16th century. And it's no joke, it's really made of gold. And it happened sometime that some students, they climbed up during night and they tried to steal some of these parts. But they did not check out that everything was controlled by video camera systems, so they could immediately identify them. And this golden roof almost works like an NIR reflector. But our area is, of course, not only known for the mountains, also for the beautiful lakes in the mountain. This is a spot maybe just 20-30 minutes away from the capital. And this kind of lake, they are also known to be to carry some kind of information about the climate that was going on during, in this case in summer, because this picture was taken in autumn. And so there is several information that can be deduced from these mountain lakes. So that was our old chemistry building that was recently reconstructed by this new one. Looks, I think, much better, no comparison. We are very happy because our former minister he agreed and signed to build this one, and the final price was more than 100 million euro. It's now very, very good, even the location here, you see here the river, the Inn River, and the building is organized in this system that's almost, there are two buildings. One building is belonging to our faculty of chemistry and pharmacy, and the second one is belonging to the medical university in Innsbruck. The university was divided several decades ago into two universities. And the idea is that you can collaborate with the partners quite easily because they are so close, which works more or less good. So inside looks like that on one side we have the laboratories, and on the other side we have the office. Everything is fully air conditioned, so the working condition is quite good, but of course money is never enough for instrumentation and so on. So I just wanted to show you these slides that you get an idea where we are. So what we are doing, we are an institute of analytical chemistry focusing on the development of new analytical techniques. Meaning we are also dealing with enrichment technologies, sample treatment methods. We're doing all the separation stuff based on liquid chromatography and electrophoresis, and also the mass spectrometry. And this, of course, very important, as we all know, for infrared spectroscopy, Raman spectroscopy, and so on. We always need highly reliable and validated reference methods. And this we combine with different sorts of vibrational spectroscopy, mainly focusing on near-infrared spectroscopy. Now, I want to go a little bit back, and I want to put the focus on several scandals that happened during the last decades. And I want to point out several very important of them. First, the milk scandal in 2008. It was in China when melamine was added to the baby nutrition in order to simulate a very high content of protein. But unfortunately, melamine is transformed into an acid in the stomach, and this can irreversibly damage kidneys. So in this case, 6 babies had to die from this. But that's not the only scandal. There are several others all over the world. So in 2013, there was the horse meat scandal. And out of 27 beef burger products tested, 37 were positive for horse DNA. And this continues. So there are one after the other, several other scandals. For example, plastic contamination in Mars chocolate. It's not very nice to have this one. And so on, and so on. And this is one of the reasons that we need new, fast tools in the field of analytical chemistry. So one trend is going towards higher performance. That's mainly achieved by the application of laser systems, quantum cascade lasers, or the approach of atomic force microscopy hyphenated to infrared spectroscopy going down to the nanometer resolution, but of course this is a very expensive approach. The other thing is going to the miniaturization for small, cheap and easy to use devices, and even imaging is becoming more and more important for fast, cheap and also easy to use high resolution spectral imaging. Now let me focus in this presentation on the miniaturization part. So today there are several instruments already on the market working on different principles, on either dispersive, or you can have tunable filters, or Fourier transform small devices. And you see from 1940 going down all the years, the devices become smaller and smaller, and some cheaper and cheaper. And even the first integrated device into iPhone was already published. So the question is where will we go and what can we do with such types of instruments? This was one of the first devices invented by Uhura Scientific Company in the United States. Later on it was bought from Thermo Fisher, and this one, for example, is based on a MEMS technology, which is the acronym for Micro Electromechanical System, meaning that in this case the according wavelengths is adjusted depending on the position of these keys, like in the piano, so you can modulate the waves. So this stuff is very cheap today to produce, and it works quite well. Other devices like the invention from GDSU, which is now the AWI solution, is a spectrometer working on a filter-based technology, meaning after this mirror, spacer mirror, you have a substrate, and this substrate simply filters out the polychromatic light so that you get the individual wavelengths. It's also very cheap technology, and in this case, especially if you want to work with solutions, and more importantly with aqueous solutions, you have the problem of the non-constant temperature, and for this reason we develop such accessoires, in this case made from aluminium, which includes here a cuvette holder and a gold mirror, so that you can, during your analysis with this system, control the temperature. You see here the light source and the detector. And in our case, we investigated a different type of problem. We checked the content of ethanol in gasoline, and by applying such a system, you see that the reproducibility can be dramatically improved. What does it mean? With such a very simple but effective accessoire, you can go down with the lower limit of detection percent from 8.6 to 0.6. So you have an improvement by the factor of 10. And at first we thought, yeah, it's a nice application, and finally now it's applied by a Shell company in Netherlands for quality control. Working more and more with miniaturized instruments, we have to consider the different wave number ranges and even the different resolutions. And for such an approach, new and more critical evaluation is needed to really understand the performance of such spectrometers. And for this evaluation, we have developed this workflow. So we use on one side benchtop instruments, on the other side miniaturized instruments. We record the NIR spectra, and then we add the quantum chemical calculation on this side. On the other side, of course, the reference analysis. We do the multivariate data analysis, the two-dimensional correlation spectroscopy, and also multivariate limit of detection. And then we come to critical evaluation. So our applications fields are traditionally medicinal plants, phytoanalysis, phytopharmacy. We do the quality control, the estimation of harvest time, provenience, food. Very important tasks are safety, fraud, fast quality control, and provenience, and we are also working a lot in the field of cancer analysis and material analysis, which I will not speak today about. So first, let me show you some examples of the medicinal plant analysis. This is the investigation of Verbena officinalis, which is used against mild to moderate cold. And the main two ingredients are verbenalin and valvascoside. And as you can see, both ingredients can be quite nicely analyzed, both with the benchtop and the handheld instrument. Why is it important to have a very fast analysis? Because this plant is growing on the island of Mallorca in Spain, and we found out that the harvest time is critical concerning the quality. So in some cases, there's a huge difference if you wait for 1 or 2 or 3 hours more or not. And therefore, it's very helpful to have such a device where you can go on the field and do an easy measurement. And we developed such a method just for this plant. Another example is the quality control of rosemary folium, and I want to give you an idea about the two-dimensional correlation spectroscopy used as the eye of the spectrometer for the visual perception. So we investigated 60 samples out of this rosemary, and you see here on the left side the 2D correlation spectrum from the benchtop device, and on the right side from the miniaturized device. And what you can see here is an outer peak appearance in the visual perception of this microphaser instrument, meaning you have here an important wave number range which is not important for the benchtop device. And no one would ever think about this, that something like this could happen, but it's reality. So from this you know that you should include this part into your regression model. This also shown here then with the regression vector analysis, that exactly this part here is important, but it is missing with the benchtop device. And by optimizing the system, you can even go down, in this case, with the error of prediction to 0.1%, which is in comparison with the benchtop device really quite good. So at this point, quantum chemical calculation is becoming more and more important. It's a very nice collaboration that I've started with Professor Saki, continued with Dr. Christoph Batch, as many of you might know him, and I have a colleague at the theoretical chemistry department in my faculty, and we together do all this investigation. It's an example, the structure of thymol, a very prominent molecule for medicinal plants. And you see here at first the experimental spectrum, and then the calculated one in a solvent, and then the calculated one in vacuum. So it fits very well. And today this technology enables you to calculate stepwise, for example, the first overtones and the binary combinations, and then to reassemble the whole spectrum. So you get a much better understanding which vibration is coming from what, and you can just identify the different overtones and combination vibrations by this. And independent on the phase state, if they are solid, if it's melted or it's a gaseous phase, you can see that in these investigations there are two spectral regions which are clearly independent of the sample state or the concentration, and they are also crucial for establishing quantitative models. So, to make the story short, what you can do is calculate such a heat map. And this heat map is very beneficial because it shows you which overtones and combination vibrations make an important contribution at which individual wave number. So this allows you to improve fundamentally the whole system. Furthermore, multivariate limit of detection is becoming more and more important. What does it mean? It means you're not working with a single LOD value, you're working with an LOD interval, meaning that for your calibration model establishment. You are not focusing on single wavelengths or narrow wavelength range, but you are using a quite broad range. And for certain applications, this should be considered, as for example, the determination of melamine in paleo nutrition. We show with this example that by applying canastone and duplex algorithm for a sample collection and applying multivariate limit of detection, you can do the quantitative analysis very sensitively, going down to a lower limit of detection of approximately 0.2%, which is in comparison again with the benchtop device really satisfying. You know, NIR spectroscopy is also capable of analyzing physical parameters and not only the chemical ones. So it's a current project we are doing in the middle of Europe. It's funded by the European Union, and the research is about new gluten-free wheat and products like this. And we were asked to establish a model that allows you to determine the antioxidative capacity of gluten-free grains. And this analysis should be able to be done extremely fast, within seconds, and non-destructive. So we did all the reference analysis applying DPPH assays and so on, and established a model. And in this case, the reference value is given as the milligram gallic acid equivalent per gram. And you can see with such a system, with an optimized calibration validation protocol, you can even do the quantitative analysis very sensitively. This is a very small device coming from Israel. It's built there from the secret agency. It's a very small device. It costs only about 400 euro. Spectra can be directly transferred onto the iPhone. But it has also a disadvantage because each spectrum you record is going to a cloud. So almost, if the instrument is very cheap, you are still also working for the company, which is really very critical. But even the instrument is small, and the wave number range is very narrow to the visible region. For foodstuff analytical purposes, it works really quite well. So I think we have to be very careful with our experiments that we don't do something wrong. It can be done very fast, and therefore we need certain strategies and claims how to do, and especially working in the aquaphotomics field, it should be not too complicated to interpret some data, and the established models should not be too artificial. I think that's very fundamental, that we should see, can we understand what we're doing, and do we have really fundamental interpretation? And so what are some future perspectives I personally strongly recommend? The first one is that, in my opinion, the development of a small and portable device, maybe based on filter technology, because it's quite cheap, can or even should be established as a kind of NIR aquameter for very simple and efficient measurement, which should be not a problem today. And furthermore, 2D correlation analysis, which could also be extended to 3D correlation analysis, would be very beneficial to show the dynamics of a system focusing on the different water signals. So you really have 100% argument that the water in the system is really different. Then quantum chemistry calculation and simulation can further support the findings which have been found by 2D correlation analysis. And as I have shown, multivariate approaches for calculating DLOD would be even beneficial to enhance the sensitivity of aquaphotomics. And as today Rumiana already mentioned, and this is in my opinion a very important point, is the direct link with different disciplines. So it should be clearly defined what is the importance and the role of aquaphotomics in different fields like cancer analysis, medicinal plant analysis, and so on. I think that's a very crucial point. If this is clarified, things will go on quite much more easier. So, yeah. With this, I tried to save some time because Sultan strongly recommended. And I have to acknowledge, of course, several people. First, Rumiana for our very long-lasting, for our very long collaboration, and even Jelena for the very nice organization of the conference and everything. And have the long collaboration with Professor Saki. I want to thank also Sultan and George for visiting us many times in Innsbruck, and you for a very nice collaboration, and also Bernhard for giving more and more input into the field. I think it's on an optimistic way. And of course I have to thank all my group members at the University of Innsbruck and for several organizations for giving third-party funding money, which is really very important. Yeah, with this overview about the application, I want to close this talk, and I hope I also could give you some ideas about my future perspectives of especially NIR spectroscopy in aquaphotomics. Thank you very much.
Thank you very much, Christian, for this excellent talk. I enjoyed a lot. Any questions? Who has questions? Okay. Yeah.
I have a small question regarding that results of comparison between the portable instrument and benchtop instrument. I don't understand how come that the portable instrument can give you some spectral feature that is absolutely not seen by the benchtop. I cannot understand how
I don't want to say that it's absolutely not seen, but it's not of importance. That's the difference. It has not this predominant role for the benchtop.
I see it. Thank you.
Next question?
Yeah.
You had the same question.
Would have been almost the same, yeah.
More question? Then I have a very general question. Talking about the trends, can we really expect to have a spectrometer in a smartphone which provides comparable results to a benchtop instrument, or what do you think about this?
This year in April I had the chance to visit Jena. Many of you maybe might know Yumebutai. He's a very famous Raman spectroscopist at the University of Jena in Germany. His group almost has 350 co-workers, so it's extremely powerful, and there are 2-3 institutes belonging to this position. And they are very close to bring this on the market. So they have it already finished in the laboratory in collaboration with Fraunhofer Institution. So the answer is yes, but I don't know when they really will now release it. But I think it's technical, it's done.
What is the application area?
I think currently they are more and more focusing on material analysis. Yeah. But they did not give me too much details about it, so just some information.
But it is Raman.
No. This one is NIR, but their main focus is Raman spectroscopy, but they are also doing NIR, MIR, whatever you can imagine. It's unbelievable.
And this device you mentioned that they are developing together with Fraunhofer, this is in the size of like built for smartphones or built in
Yeah,
the...
it's
really built in
constructed
smartphone?
for smartphones.
Okay.
Yeah.
So that's small. Okay.
Yeah, very small.
Thank you. More question?
Even they already had one press release, I think 1 or 2 years ago.
More question? Then I have a last one. We have been working on Aquaphotomics to extend the application and invite more and more people. So for new laboratories, it might be a good idea to think on cheap instruments. Do you have any advice? What spectrometers could be used the best in the field of aquaphotomics?
Yeah.
Difficult question, I know.
I don't get money from the companies for this, but based on personal experience, the cheapest one currently on the market is SIO from Israel. It's really cheap, but you have the problem that you give all your data away. So normally one should keep distance from this one. The next one we are working a lot is from the Awaji Solutions. It's this filter-based, quite small instrument. We have some kind of collaboration with them, and after we developed this accessoire for temperature control, they came up with some similar system. The point is that this instrument, when we bought it, we paid €8,000, and now almost the same instrument, but the next generation costs €25,000. And speaking with the boss of the company, she said to me on the phone, yeah, the reason is very simple, because we can sell so many of the instruments easily, even the price will go up. So again, it's a question of money, how much you want to invest, but I think SIO is currently, from the small instruments, one of the best, but you have to give away your data, and the Awaji solution, I think, is a really very solid and good instrument.
Thank you very much.
Thank you.
Yeah.
Thanks again.
One more thing, SIO was in the second overdose region of water,
Yes,
from
yes.
740 to
9 something,
40
yeah.
nanometers. But if you want to go further into the first overdose, then we have got DLP Nano, the telescope. It is $1,000.
This can nano, yes.
Yeah, dollars.
It's about $1,000.
900 to 1,700.
But there's another problem with Spec. Currently, they have problems with the production.
Yeah, we don't need to talk about the aspects. There is a company, so the know-how comes from TI, and the instrument is available on the market, not only from Tespec.
So several advantages and disadvantages.
Thank you very much, Professor Rupp. Let's thank him.